I decided to do a pattern detector or a sequence detector using two possible sequences. So throughout my presentation, I'll be going over the objective, some specifications, state diagram, state table, K-map simplification, and comparing the various hardwares to see what's the best possible design choice. So my objective was to design a sequence detector using two possible sequences, either 1110 or 1101. So since there are 4 bits in the sequence, there will be 5 states per Mealy machine. So I chose to do the Mealy machine based on it using the least amount of states to make my design simpler. So I had some specifications. So there is overlapping allowed by 1 bit. So for example, if I had the input 111011, then 2 different sequences are detected. So I wanted to also use the Mealy machine because the output must go high once the 4th matching bit is detected. So the input is given as defined as x, and x is the value of the input line in a clock cycle. So here is my state diagram. I'm using 5 different states. So you can see it go through each of the states to detect 1110 and 1101 in blue and pink respectively. So here's my state table. From S5 onward, I just used don't cares because nothing was happening there. And you can see how the output Z goes high twice, which is when the 2 different sequences are detected.
Jillian, can I just ask a question? Can I just ask something? I think you're going too fast over your diagram, your table. Do you mind if you just leave it on for a bit in case people want to see exactly what's going on?
Yes, of course. Is this slide good?
That's good. Yeah. I mean, maybe others could see it that quickly, but I couldn't. Just, if you don't mind, just let's look at it before we go. I mean, there's no rush. You don't have to run it that fast.
Okay.
So, do you want to walk us through your diagram, or shall we just look for ourselves?
Oh, I can walk you through. Okay, so my first state, which is the reset state, so that's S0. So either when x is equal to 0 or x is 1, it'll either map back into itself or go to S1. So both of the sequences start with 1, 1. So they both kind of follow the same pattern. Until they get to S2, they branch in different directions.
So what does S1 represent?
The first state, it just basically, yeah,
It would just be 1, right?
yes.
Okay, so if S1 just tells us that we have gone 1 bit by just 1, presumably S2 will give us 1, 1,
Mm-hmm.
and S3, 1, 1, 1, and then S4 is 1, 1, 1, 0.
Yes, that's correct.
Mm-hmm.
So once it branches out into 2 separate directions, it either is equal to 1, either 2 different sequences in the diagram.
Right. Okay. So when you get, I mean, you may be right. I'm just kind of puzzling whether when you go from S4 to S1 and you get an output, would that work?
Going from S4 to S1, that just goes back to S0.
I wonder if, you see, obviously with S4, you will have an output for your first kind of key. That's 1110. but I'm not sure if 1101 would result in an output there at S4 after 4 states.
Well, it seemed to work when I did my actual design.
Oh, it does?
Yes.
Fine. Okay. So let's proceed. Yeah.
Okay. So here's my state table, and I implemented that based off the state diagram.
Very good.
So you can see that S5 onward or just don't cares because I'm not using them. So here's my K-map simplification to Boolean expressions. So the equations are relatively simple. And so for my design, I first wanted to look at different flip-flops to see which one uses the least amount of parts. So I looked at D flip-flops, JK, SR, and T flip-flops to see which one would use the least amount of parts. And here is my state table for using D flip-flops. So it is identical to the original state table. And the simplified equations. And here is my circuit for D flip-flops. I'm using, in the first design, which is on the left, I realized that there were some parts going unused, so I got rid of them, and I reduced it down to 6 AND gates, 3 OR gates, 3 D flip-flops. And here is I tried using next JK flip-flops just to see what that would look like. And here are the reduced equations. So it uses more equations, but it comes out simpler when I implement it in Logisim. So compared to D flip-flops, it uses less gates, less OR gates, less NOT gates, same amount of flip-flops. So here I tried using SR flip-flops, so it's a similar concept. I just followed the excitation table for SR flip-flops and got my equations. And here's my circuit for SR flip-flops. So they're all sort of the same, except they use a different number of parts based off the flip-flop being used. So here I use T flip-flops, and similar concept, nothing really changes here. We still have the same amount of the same equation for Z, which is the output when it goes high. And here is my circuit for using T flip-flops. So comparing all the different flip-flops, I realized that JK flip-flops, it uses the least amount of gates. So compared to the rest. So I assume that least amount of gates means least amount of power. Does anyone have any questions up to this point?
Hey, Jillian.
Yes.
Hey, I was curious on the circuits
Oh, yeah.
that you had up there. I was just curious what the 3 squares on the right side were again.
Oh, they're just
Flip-flops?
flip-flops. Yeah,
Okay, wonderful. Thank you.
of course. Okay, so next I just wanted to look at the different ICs being used just to compare the different ways I could implement this design. So I used 4 16-to-1 multiplexers to design this, and 3 D flip-flops. And then again, I simplified it more to use 8-to-1 multiplexers, so I used 4 of those. But I really didn't want to use multiplexers. I wanted to go towards programmable because I felt that that would make more sense for what I have, and I'll go into that more later. So I tried to use Decoder just to see how it would work, and it ended up becoming very messy, and it didn't work because all of the output pins go unused and they're unnecessary. So there's no point in using a 4 to 16 traditional decoder. So next I considered programmable devices. So with programmable devices, there's more flexibility in the circuit, faster design times, there's fewer components used, fewer parts used, reduces inventory costs, so you have to keep less parts in stock. So in low volumes, programmable devices are much cheaper compared to mass producing traditional circuits. So there's fast design turnaround because of this, and there's simpler and more available development tools. There's a lot of free tools for designing programmable devices. So the first programmable device I looked at was an FPGA. So researching online, FPGAs, they cost between $10 to $300. The one we use, the Nexus 3, $70 or so. So they're good for design requiring large amounts of logic. But because my circuit is relatively simple and doesn't use a lot of logic, I decided to steer away from this, but I still wanted to show how it would be used for my particular design. So there's large propagation delays with FPGAs, which is the time it takes for the signal to get to the output. And they're generally unpredictable because you could be designing the whole circuit and then get to the end and it doesn't work. And you have to go back in and it's more complicated. So here's my code when I just tried to do this to see what it would be like. So I basically just followed my original state diagram to do this. So I still have 5 different states, and I map through each one. Either if the x in is 1 or if it's 0, so it can either go 2 different ways, 1 or 0. And then in 2 cases, the x out is high, which is when the 4th matching bit is detected on my sequence detector. So when either 1110 or 1101 is detected. Does anyone have any questions about this or anything? So I'll move on. So I created a test bench for my code to see if it works. So the XIN I used was 01011101, and that would reset. So looking at that, that would, because I'm allowing 1 bit overlapping, it would detect the sequence twice. So here is my test bench result. So the clock, the XIN, which was, I showed you before, right here, what I had in my test bench code, and the X out goes high twice in the first cycle. So that means that the sequence was detected twice with 1 bit overlapping allowed. So I next looked at the programmable array logic. So that has programmable and fixed OR arrays. So with programmable devices like PAL, there's lots of free designing tools. It uses simple combinational circuits, so simple logic combinations. So what I'm using would be ideal for it. PALs are mostly designed using state machines, truth tables, and Boolean logic equations, which is what I'm using. So the price, they range from $2 to $15. So they're much cheaper compared to FPGAs, and there's low propagation delays. So these are all the pluses of using a PAL. So here is my drawing. I just wanted to draw to see how it would look. Because on Multisim and Logisim, they don't offer actual PALs to use, I ended up just drawing the hardware inside of PAL to show how it works. And I used D flip-flops to do this. So I ended up using this design because I believe that it was the simplest compared to using traditional ICs, because ICs are sometimes not available and they waste space on a circuit board. So I thought this would be the best condensed version of my project. So same circuit, but I did it on Logisim, and I'll show you it actually working in a bit. So I still use the same 3D flip-flops. And so the input X is just the input that the user puts in, so a random sequence, and I map it through with the clock cycle. And when it's detected, then X goes high. So the reason I chose PAL over ROM is because, as you can see, I just drew it out. I didn't actually implement it because I was already deciding on using PAL. But you can see all the min terms that are being wasted and unused. So I didn't see the point of using this if so many of them go unused. So ROM is traditionally good for storing large amounts of data, but because my circuit is pretty simple, it doesn't need to store that much data. So I narrowed it down into 2 different possible circuits, using the JK flip-flops with the traditional AND and OR gates and NOT gates, or using a PAL. So these are the 2 different circuits that would work that I could use. Does anyone have any questions?
I guess one question, what would be the difference between the PAL and say one of the $10 FPGAs?
Well, PALs are much cheaper, and using an FPGA, something might go wrong using that, and then what other FPGAs are you talking about?
Because you mentioned earlier that like the FPGAs could be as low as $10. So like what would be the difference between saying using the $10 FPGA and one of the higher end PALs, which are like $15 or so?
Well, I would be using a pretty basic PAL, just the mass-produced series. Using a more expensive one would maybe a more complicated circuit, but maybe be using a reusable PAL. Or does that answer your question, Israel?
Yeah.
Okay.
Plus the fact that FPGA is volatile and you have to keep it on, or I don't know, maybe you have to have a ROM somewhere else to store the data so that run it on FPGA at any time required. That would be the other issue, right?
Yeah. Okay, so if there's not any more questions, I'll move on. So still comparing using JK flip-flops versus using PAL. So JK flip-flops, just looking at it, looking at the circuit, they use less parts than PAL, but really the PAL is condensed into one single programmable device. So it's really actually less parts being used. So PALs use less board space, and they're faster and traditionally have lower power requirements. And they have a cheap assembly process, high reliability, so they use fewer ICs and less circuit connection. So instead of soldering parts, if I was actually doing this in an actual circuit, it wouldn't be necessary. It could be used in a small design. And there's lots of free design software or reduced design software to design this. So hence, looking at all the different variables, it's better to use PAL versus ICs like JK flip-flops and OR gates. So here is just the actual circuit working for PAL. So my X input is 1110111010, and that's just random. And you can see it's working with a 1-bit overlap, and that it'll detect the sequence 4 times. So the LED, which is just connected to the X output, should light up 4 times. So I just mapped it through using the clock, and it detects either 1110 or 1101. So does anyone have any questions about?
Is this run on multisim?
Oh no, I used Logisim. My multisim trial expired, so I had to use something else.
This is Logisim.
Yes.
Yeah. Okay.
Okay, so again, summarizing why I chose to use PAL. It's theoretically less expensive than a standard IC looking online. And for non-complex designs, PALs are most suitable compared to a ROM. They're easy design changes. So say if I wanted to change something about what I was doing, change either the sequence or add to the sequence, then it would be simpler than taking apart the entire circuit. And it can be used to replace messy off-the-shelf components that might not be available. So standard ICs might not be available, and it would make more sense to use PALs, which are mass-produced. They're user programmable, they minimize turnaround time, and there's lots of free software available to do this. And there's quick system designs with reusable PALs. So in summary, the PAL configuration is best because it's less expensive and easier to use. They're very simple, easy to understand, and they work best with my particular design. So for non-complex designs, PALs are best. They replace ICs and other components just by using PALs. You can have a smaller circuit and use all the circuit board to the best of its ability, and it can quickly test and implement. You can quickly test and implement using PAL, so you can design different circuits, and it's easy to test it and see what went wrong. Whereas using FPGA, it takes a while, and it's difficult to go back in and troubleshoot. So that is the end of my presentation. Does anyone have any questions?
I'll wait to see if there are any questions from the panel. If not, then yes, I have 1 or 2 questions.
Yes. Oh, I'm sorry.
Well, there seem to be no question.
I have a question.
Sure.
When you earlier on one of the slides where you had the video,
Yeah.
did you pre-input or like you had to program it in or something? The input?
No, I used a button on Logisim. They have a button where you could just either go 1 or 0.
Oh,
so I
okay.
can show it to you
Okay.
again. Yeah, so I just it goes through the sequence, just mapping out with a clock cycle, so through the D flip-flops.
Oh, okay. Okay. I was wondering that was my question earlier. I was going to ask it, but I didn't want to interrupt.
Oh yeah, of course.
Okay. Thank you very much.
Sure.
Any others? Right, Jillian. Can I ask you to go back to the very beginning where you tried D flip-flops and then went on to JK flip-flop for the very first time? Right. So this was that you used these gates.
Mhm.
The output of these gates were fed onto a D flip-flop. Am I right?
Yes, that's correct.
And so for example, product 1, product 2, product 0, and that's why you use D flip-flop.
Yeah, I didn't end up using D flip-flop because I compared them all and I saw which used the least amount of gates.
Okay. So then when you went to do JK flip-flop, can we, right? So your gates were reduced by so much.
Yes.
Right. I see. Okay.
Some of the equations were similar, so I ended up, it was easier to connect the different equations.
Right. My question was that, well, not the question. I'm just trying to, by asking you this, I want other people to see that these flip-flops could actually work as the hardware for your total design.
Hmm.
They could be used as hardware.
Instead of using PAL or
Oh, exactly. Right.
okay.
Yeah. Which we never tried this. We never, in the entire course, we were talking about using flip-flops as a form of storing data to feed back to our model.
Hmm.
But you're using these as actual hardware, just like the MUXes or decoders or the programmable, any of that.
Yes.
So it seems as maybe, I mean, in your final comparison, I didn't see you comparing PAL or FPGA with JK flip-flop, did I? I mean, did you?
At the last slide, I went over some of the pros and cons of using JK flip-flops versus PAL. I can go to it.
Did I miss that? Okay.
Yeah. So I reduced it down to 2 of the best circuit designs that I could find. So on the left, that's the JK flip-flop design, and then on the right, it's PAL. And then
So how did these two compare? So I missed that out.
well, using JK flip-flops, looking at it, it uses less gates, but using a PAL it's cheaper to do. PALs use less board space, and instead of using unnecessary, like things could not be available, so it'd be easier just to use PALs. They have high reliability, and as I said, there's free designing software for PALs.
Mm-hmm. Plus the fact that for $15 you could buy PALs which would be registered output, and you wouldn't need extra devices like the flip-flops or JK flip-flops.
Yeah, I just looked at a basic PAL system, so just
Okay, that answers my question. So are there any comments, any question from anybody from the panel? No.
I got no questions at the moment.
Please go. Oh, you have no question. I'm sorry. I thought you said you did. Okay. I'd like to make my comment, my final comment about your presentation, Gillian. And I want to know if everybody agrees with me on making this comment. I am absolutely satisfied to see that how brilliantly you utilized your entire knowledge of this course in designing, not only designing something which is very useful, you presented it in the most efficient and brilliant way that we all enjoyed so thoroughly and beautifully. I'm only expressing my own feeling. I don't know if anybody would agree with me. I hope they do. But you did a fantastic job. I'm not
Thank
joking.
you so much.
I honestly think that I'm really pleased that you're the first one who presented, and therefore you set a true example. I hope for others to see how it should be done. Not only you did it in the right amount of time, you spoke so clearly, so to the point, and everything that you said, you had something to show for. You had your slides in most pleasant way, the color, the shape, the writing, how it was done. I'm just amazed at how beautiful you've done.
Thank you so much, Dr. Kasai.
And I want to gladly, I'm pleased to tell you that now you're exempt from the final exam. You don't have to take your final exam because you know your design, you know everything there is to know. So why am I going to examine you? So thank you very, very much, Gillian.
Thank you. It's great to hear. Thank you.
Right. Does anyone want to disagree with what I said? I know you don't normally, but
No, I totally agree with you. Fantastic how she went through all the designs, every idea, the different types of flip flops that you could possibly use, and use PAL and RAM, and said why you couldn't use why you could, but why would it be convenient to use certain ICs and logic gates. It was really fantastic. It was really great that she went through everything.
Thank you so much, Eric.
And you're so right of your final choice too, because PAL for this design seemed to be the best choice. I mean, it's just one IC. What better than that? In terms of power, in terms of cost, in every sense. You could actually sell this design. Great. Thank you very much.
So I'll stop screen sharing.